Welcome all, I am T.Y.B.Sc from SSR College Silvassa. In this tutorial, we will talk about uniform continuity. How to use this video? This video can be effectively used if students write down the contents of tutorial in the notebook, read it 2-3 times and then follow it from video. The contents of tutorial is available in PDF with title Uniform Continuity on the following link. Definition. Let xd and y row be metric spaces. Let f from x to y be a function. We say f is uniformly continuous on x. If given epsilon greater than 0, there exists a delta greater than 0 depending on epsilon only, such that for any x, x naught, x dash belongs to x, and distance between x and x dash less than delta implies row distance of fx and fx dash is less than epsilon. Remark, uniform continuity implies continuity, but converse is not true. Example. Give an example of a function which is continuous but not uniformly continuous. Or, consider Ru and define f from R to R by fx is equal to x square. Then show that f is continuous but not uniformly continuous. Solution. As fx is equal to x square is a polynomial function and we know polynomial function is continuous, so given function is continuous. Now we shall show that f is not uniformly continuous. Consider epsilon is equal to 1. We shall show that for epsilon is equal to 1, no delta greater than 0 works. For delta greater than 0, let x1 is equal to delta by 3 plus 1 by delta and x2 is equal to 1 by delta. Then modulus of distance between x minus x2 which is equal to delta by 2 is less than delta. But modulus of fx1 minus fx2 which is equal to delta by 2 plus 1 by delta whole square minus 1 upon delta square which is equal to delta square by 4 plus 1 which is same as delta square by 4 plus 1 which is greater than 1. Thus, for any delta greater than 0, we have points x1, x2 belongs to R such that x1 modulus of x1 minus x2 is less than delta, but modulus of fx1 minus fx2 is greater than 1 which is equal to epsilon. Hence, f is not uniformly continuous on R. Example. Let xd be a metric space. Prove that the function d is uniformly continuous. Solution. We know d from x cross x to R is a function. Consider product metric d bar on x cross x. Then for x is equal to x1, y1 and y is equal to x2, y2 belongs to x cross x, we have d bar x, y is equal to d of x1, x2 plus d of y1, y2. Let epsilon greater than 0 be given. Let x is equal to x1, y1 and y is equal to x2, y2 belongs to x cross x. Then we have modulus of dx minus dy is equal to d of x1, y1 minus d of x2, y2. Equation number 1. Now, d of x1, y1 is less than equal to d of x1, x2 plus d of x2, y1 using triangle inequality, which is less than equal to d of x1, x2 plus d of x2, y2 plus d of y2, y1 again using triangle inequality. So that we have d of x1, y1 is less than equal to minus d of x2, y2 is less than equal to d of x1, x2 plus d of y2, y1. Equation number 2. Similarly, we can show that d of x2, y2 minus d of x1, y1 is less than equal to d of x1, x2 plus d of y2, y1. By 2 and 3, we have modulus of d of x1, y1 minus d of x2, y2 is less than equal to d of x1 comma x2 plus d of y2 comma y1, which is less than equal to modulus of d bar x1 comma y. Hence by 1, if we take delta is equal to epsilon greater than 0, then d bar x comma y less than delta implies modulus of dx minus dy, which is equal to d of x1 comma y1 minus d of x2 comma y2, which is less than equal to d bar x comma y, which is less than delta, which is same as epsilon. Hence, D is uniformly continuous on x cross x. Theorem. Let x be a matrix space and A is a subset of x. Then the function f from x to y, x to r, given by fx is equal to d of x comma a, that is distance between a point x and the set A, x belongs to x, is uniformly continuous. Proof. For all a belongs to capital A and xy belongs to x, we have by triangle inequality this d of x comma a is less than equal to d of x comma y plus d of y comma a. By taking infimum, we have infimum of dx comma a over all a belongs to a is less than equal to d of x comma y plus infimum of dy comma a over all a belongs to a. This implies, by definition, distance between x comma a is less than equal to dxy plus distance between y comma a. This implies d of x comma a minus d of y comma a is less than equal to d of x comma y, equation number 1. By interchanging x and y, we get d of y comma a minus d of x comma a is less than equal to d of x comma y. Thus, by 1 and 2, we have modulus of d of x comma a minus d of y comma a is less than equal to d of x comma y. Now let epsilon greater than 0 be given. Then taking delta such that 0 less than delta less than epsilon, we have modulus of fx minus fy, which is same as d of x comma a minus d of y comma a, which is less than equal to dxy less than delta, which is less than equal to epsilon. Hence, f is uniformly continuous.